Thank you for that great introduction, and thank you to everyone who's working behind the scenes at this conference. It's been great. So I'm here today to introduce the Quantile Cube approach, which is basically a way to understand movement dynamics in athletes, and specifically we're focused here on elite female athletes, so we kind of define that as collegiate and professional women's soccer players, since that's something that's underserved and under-researched, and something that's important to me. And this is my work with my advisor, Dr. Jan Hanig. And so let's kind of dive into what the problem is that we're kind of trying to solve here. So wearable devices have really grown in popularity, and no matter what company you use, you're getting out lots of information. However, a lot of these traditional metrics are pretty arbitrary, so they're using a threshold to define what's an acceleration, what's a sprint event, or how are we defining our training load. And then you run into a problem, I want to switch companies. One company offers me a better deal on these devices. And at the college level, we're all about saving money. And so then you're kind of starting from square one. So if I told you two players had the same training load, how do you know what that means? For a defender, that's going to look completely different than a forward, right? And so it's going to depend on what you're doing in a game. And research has shown that movement patterns do vary across positions, match periods, so half to half, genders, competitive context, playing level, environmental conditions, altitude, all of these things play an impact. And so can we get a better way to understand these patterns? So effective athlete monitoring is going to require us to develop an interpretable and data-driven model that kind of allows us to capture these differences. So our goal we set out is to build a framework that captures the distributions of movement. So here you can see on the left is the first half, right is a second half heat map of just player movements. And you can see just by eye test, those look very different. So the solution that we're proposing is what we're calling the Quantile Cube, and that's what I'm going to talk about today. And I'm going to talk about several applications and how this can be used and expanded upon. So we obtained raw GPS data filtered to 9 female athletes once we looked at playing 25 minutes per half in over 5 matches of the season. And so yes, this is a relatively smaller data set, but we wanted to have enough data to be able to make reasonable conclusions and assumptions, right? And so we had 9 female athletes across 23 matches in a season. And for each of these, we had a sample that included one time point of a timestamp, a longitude, and a latitude for every second of every game and every practice for these 9 athletes. And so you can imagine lots of data. Now, not all 9 athletes played in 23 games, so we have what we're going to call 396 unique athlete match halves. So that's a unique athlete per match per half. That is not 9 times 23 times 2. I will tell you that right now. And so for each of these, we took their raw data, and we converted this longitude and latitude to meters, and then we fit a spline, so basically we drew a line through these points, and we fit a 3rd degree interpolating spline. And if we think back to our calculus, we can take derivatives, right? So your first derivative is going to give you that velocity, and your second derivative is going to give you the acceleration. And then you can calculate the angle of movement by looking at the difference between that vector for velocity, the vector for acceleration, right? Very basic, calculus physics, but it gets us some information that we may not have just from that raw GPS data, right? And that was fit at 10 points per second, so we're getting a little bit more granular with that movement. So then from here, we're going to create what we call the Quantile Cube. And so this is our 3-dimensional summary representation of this movement. So working with this raw data is going to be very hard to work with, right? Lots of information, very overwhelming. But if we can get it into a form where we understand it, it's going to be a lot more valuable to us. So here we're going to take our 3 dimensions, velocity, acceleration, and angle, and we're going to form what we call the Quantile Cube. So we can take 5 quantiles for velocity and acceleration. 5 gave us a good amount of points per each slice, but that is something that could be adjusted with future work or if you're applying this in your situation. And we took 4 quantiles for angle. The reason we chose 4 for angle is you're looking at the 4 cardinal directions of movement. So forwards, right, backwards, and left. This will make a little bit more sense when we look at the visual representation. So from there, we can kind of bucketize all of our movements. So you take every single movement and you just put it in the bucket. So maybe it's in the first quantile of velocity, second quantile of acceleration, moving forward, right? So that's 1 point there. And so you can take this, and for every single data point, you can put it in one of these buckets. And so if you think about it, 5 times 5 times 4, we have 100 dimensions. And so we're getting a big vector that's 100-dimensional. That can either represent our total amount of time, so our total amount of time that we moved, or if we divide by the total, we can get a proportion or percentage or a probability of being in a certain movement category. And so all of this put together, we have what we're going to call our data matrix Y, which has 396 rows because we can form one of these cubes for every athlete match half. And it has 100 dimensions or 100 features, each representing a combination of an acceleration, a velocity, and an angle quantile. So that's kind of setting up our data representation. If you're lost, we can look at it visually. So this is what we call the visual representation of the Quantile Cube, where we're pulling out that bottom corner just to look at it a little bit clearer. So here we can see that first we have along our x-axis our velocity. So Q1 being our slowest velocity, Q5 being our peak velocity. Same with acceleration along the y-axis, Q1 being our slowest acceleration, Q5 being our fastest acceleration. One thing I do want to note is that these quantiles were only coming from our full data set, but only from games. So you always want to train to perform on game day, right? So we want to mimic, the game situations in practice. So can we look at this in a practice and see how we're mimicking games? And so that was kind of the ultimate goal with using only game data to come up with these quantiles. And like I said, we used our full data set to determine our quantiles just because we did have such a small data set. But you could do it at the player level if you had enough data. You could do it at the positional level, things like that. So going back to this, then within each quantile, we have these triangles. Your triangles represent your directions of movement. So that Q1, or that top triangle, represents moving forward. Q2 is moving right. Q3 is moving backwards. And Q4 is moving left. So within each quantile for velocity and acceleration, we have our 4 angles. Then you have your color. Your color represents your density, or the amount of time you spent in that area. So in this case, it's the proportions. They total to 1. You could equivalently do percentages, things of that nature. So this gives us a really quick visual to understand how our player was moving in a specific instance. And this one being athlete 5 in match 10 in the first half. They spent a lot of time moving left at high velocities. Maybe that's a positional thing. Maybe they're coming back from an injury favoring a side. These are questions that you can then give to your staff, right? So we also had some covariates that we're going to use to kind of do some further analysis. So for each athlete match half, we have several match level and athlete level covariates that we're going to talk about today. The main ones that I'm going to call out are we looked at first and second half, playing time, and position. We also had, goals scored and conceded, score differential, results, locations, all of these things. But in our case, we didn't really look at those as much because this team won almost all of their games except for one. So it was kind of hard to use that as any indicator. Okay. So we kind of went through a 3-step process. Some of this is more to kind of justify what we were doing and to make sure, sanity check. And then some of it was to see what more can we do. So the first is we just looked at quantifying differences. Can you give me a score that tells me the difference between 2 cubes? And can we do that between match halves and see if they're significant? Second, can we reduce the dimensionality of these movement patterns and understand what's important in certain match contexts? And then lastly, can we model these distributions, because ultimately it is a probability distribution, right, as a function of our covariates that we have. So quantifying differences, I'm not going to get too into the stats, and if you want those details, I'll show you the paper at the end. But basically, we used a resampling-based hypothesis testing method, and the main issue is that there are high dimensionality and complex dependent structures within these cubes, right? More time spent in one triangle means less spent in another, inherently, because you're only playing a certain amount of time, right, when you control for playing time. So for this, we used what we call the Hellinger distance metric. If you're not familiar, very similar to an L2 distance, but it's bounded between 0 and 1, and it's symmetric. So if you do the difference between A and B, it's the same as the difference between B and A, right? And so here we can say that this just gave us a great baseline starting method. I think eventually we would like to use something that's more like spatially dependent as well. But it was a good metric to kind of get started with understanding this. So we looked at resampling-based hypothesis testing And we used a multiple testing correction because, once again, you're testing over several players over several games. But we did see that there's a significant distributional difference for every athlete match pair, basically showing the way you move in the first half is significantly different than the way you move in the second half. Now, if you know soccer, probably very obviously true, right? But it does validate that this method is showing us something, right? We are able to put into stats what we can see with our eyes. All right, so next we looked at reducing dimensionality. So we looked at applying principal component analysis to basically look at capturing the key variation to explain our movement patterns at the match level and athlete level characteristics. So 90% of our variance in our data set was actually explained by only 7 of the triangles in our, or 7 principal components. And each of these principal components were then plotted against match and athlete level characteristics to understand how these impacted. And so there's not always useful interpretation with each of the variants explained, but we did see that 2 really pulled out certain match situations. So principal component 1 pulled out a lot more negative scores for the second half of the first game of the season. And in that, we see that in this specific instance, they spent less time in those middle quantiles of velocity and acceleration in the second half of match 1. Now, that could be they weren't game fit, first game of the season. There's a lot of other explanations, but this is just something that I can call out and maybe tell, coaching staff or performance staff, and they can give context of the game a little bit better. Additionally, second, we see in principal component 4, the last game of the season, match 23, their scores were a lot higher in both the first and the second half, which showed increased time spent in low velocity, high acceleration movements. Now, one thing to note, this was a season-ending game. Additionally, it was played at a higher altitude than all the other games in the season. Is that maybe why this is? We would need more information to know, but those are just some things to think about, right? But we can see that we can call out certain areas in certain contexts, right? Additionally, we then looked at fitting what we call a Dirichlet-multinomial regression. Basically, this is a model that can be used to have covariates predict probabilities of certain counts. So we're relating the multinomial counts to the probabilities in a Dirichlet model, right? And so our optimal model out of all our covariates that we looked at was using match half, player position, and mean-centered log playing time. Basically, we're just getting it down to a smaller number so it doesn't impact the model a ton. So in these quantile cubes, you'll notice they're a little bit different looking in terms of the colors. Basically, blue is negative coefficients, red will be positive coefficients, and if it's grayed out, it means it was not significant. And so because we have 100 coefficients, this makes it a little bit easier to look at. So in the second half, you can see that all of the coefficients were significant, and they're all negative, meaning that we are spending less time in these areas in the second half. That may be attributed to fatigue, may be attributed to game circumstance, but you can see especially in quantile 5 of velocity, so those high velocity ranges, we're spending less time there in the second half. And then if we look at playing time, we can see that especially in Q1s of acceleration and velocity, we're spending less time there as we're playing more minutes. So it's interesting. Maybe your players that play longer minutes are fitter. Things to think about, right? So that's where you need more context. Additionally, we looked at position. So defender was treated as a reference category. So both of these coefficients are in with respect to defenders. So we can see here we get clear kind of positional differences, and they are in line with what we would kind of expect. So on the left-hand side, we have midfielders compared to defenders, and we can see they spend more time in these low acceleration, low velocity, high acceleration, high velocity areas than defenders, which may be, more typical of a midfielder running up and down the field rather than a defender, right? And then we also see forwards are spending less time compared to defenders, especially in that middle velocity range, right? And so especially also forwards are moving left to right less than defenders as well. And so one thing that this data set, because we only had 9 athletes, we didn't look at like wingers versus central midfielders or center defenders versus outside backs, which could be definitely something to look at furthermore. But it just shows that you can even see positional differences. And so all of that to be said, we were able to successfully capture multidimensional workload dynamics through this model, as well as offer ways to see significance between halves, as well as contextual movement signatures for certain players. And this framework enables probability-based monitoring, as well as integrating further spatial, temporal, and contextual data in order to better improve training and recovery. And that's kind of the next step of what I'm going to talk about now. So I now work with a women's professional team, and we have implemented this in real time. So this is a dashboard that I have for them. Basically, they can filter by position, training day, game day, athlete, period, and then there's also some other information I'll talk about in a second, to get these cubes. On the left and the right, you can see there you have two different cubes they can compare. So you could look positionally at a player for training. You could look at a player in training compared to their match day. Are they reaching those thresholds that they reached on match day in practice? Did you want them to? You know, are we training in preseason the way we want to be in order to be ready for game day? Those types of questions can we ask. Additionally, we can look at like one of our forwards compared to our forwards as a whole. Are they training the same way? Do they need to be training the same way, right? We can look at signature profiles. And so from that, we can develop, actionable alert systems if we're deviating from our normal, or actionable metrics. And so with this, we also are collaborating with our performance staff and our training staff to integrate further covariates. So we're looking at RPE, we're looking at menstrual cycle, we're looking at, injury data, we're looking at their daily surveys they fill out of soreness, readiness, all of these things. And can we then see how did they rate it in RPE? So what was their rate of perceived exertion compared to what they actually did? And maybe we're indicating certain trends depending on how they're rating it versus what they're actually doing. And so we are able to collaborate directly with our coaching and performance staff to give practical feedback for them to be able to look at these. So I just provide the tools. They do the kind of analysis and interpretation because they're with the athletes on a day-to-day basis. I am not. And so that's kind of where we're going. Additionally, this team has units that have IMUs in addition to GPS. So we're able to really improve the methodology of how the splines are fit and how the quantile cubes are built from the first place to make them a little bit more accurate since we have additional data. And so from there, I would like to acknowledge the Applied Physiology Lab at UNC for providing the data for the original work, as well as the professional women's team that I'm working with for their data collection and support in this project. And this is the full paper if you want to read it. It's in review, so if you find errors, please let me know. And that's my email and website if you have any questions. So thank you.